Okay. Okay, so please scan the QR code and we will start immediately. And for those of you who take the makeup exam, I will let you know the results maybe after 1 week. Okay? After 1 week. Okay, for for the schedule, okay, for the schedule for our class, we still have 1 week. Next week. So next week we still have at least Monday and so let me write here. So January 3rd January, 3rd January, and January 7th, we will still have a class. Okay, but on the January 3rd, as I mentioned, we will have a quiz on chapter 6. Okay, quiz on chapter 6. And on January 7th, uh, because this is actually, we already have uh, final exam week. Okay, final exam week. So final exam week is from 5. So January 7th, we will be, I think we just be an online class. Okay. And the rest is, if you think we need a class on January 10th, just an online class, okay, we can have this. Okay, this is, I think, for maybe review. Okay, so it's optional, okay, optional for you. But I still open the online class. You can still come. This will be a review. Okay. January 7th. Oh, yeah, I think better 3rd January, better January 3rd, so that you can have some time for preparing your final exam. Yeah, I think better this way. If you have on 7, uh, you will have more too much work to do for final. So I will help you providing some exercise for final exam. Okay, so we still have several sections on chapter 7, probably 2 or 3. Okay, I hope I can finish today and next uh, January 7th, okay, or January 3rd, and we can focus on the last day on our class for reviewing uh, and preparing the final exam. Okay, I hope we can prepare final exam. It's final exam preparation. Okay, I will mention later in the Moodle, okay, for a reminder, as a reminder. So we will still have a class next week, and also optional class, additional class for reviewing material. And I think this week I will upload one video or maybe 2 video about chapter 6 and maybe some of chapter 7. So you can also prepare some exercise for chapter 6. Okay, chapter 6. Okay. Uh, okay, I think we can start on feedback results. Find the volume region bounded by the given curve and rotate it about the specified line. So this is the questions. This last one here. So you have the curves x equal y minus 3 and then squared, x equal 4, and rotate about y equal 1. So if we try to make it in a graph, I hope you didn't have any difficulty for drawing the graph. Okay, so the y minus 3 squared here is basically from y squared and then move upwards 3 units, right? So this is 3, this is 0. And then you draw the x equal 4. And then to get the intersections, we can equal both x equal 4 and x equal y minus 3 squared. This is what I found. That is y is equal 5 and y equal 1. Okay? And then, because it's rotated on y equal 1, if you look at this is y equal 1 here. So whenever you have this kind of graph and you need to rotate, the this method will not work. Okay? The this method will not work. So what you need to do is you need to make the shell method. Okay, so take this rectangle. Okay, and for our case in this problem is dy. Okay, so this will be the dy. Rotate about y equal 1, and we need to define the radius and define the height. Okay, the radius we get it from we have y equal 1 here, right? Y equal 1 here. And this is the curve. Or in our case, this is y, right? This is y. So we can have our radius is y minus 1. Here, our radius is y minus 1. And then the height itself is the function of y, right? Is, or the function of y is actually here, and we have x equal 4 at this point. So the height is 4, okay, minus the curve. The curve is here, right? The curve is on here. This is the curve, right? This is the x, right? And this is the y. So the height will be 4 minus the curve, the x. Okay? Or in our case, we need to convert all with y because we are going to integrate with respect to dy. Okay. And the problem here is, I think, just the calculations that you need to think. Yeah. So the formula 2 pi r and then height and then dy. And we can expand the squared, multiply each element, multiply each variables, and we are going to have this equation here. Integrate, and I think this is quite troublesome, I think. But actually, what I can do offer is this is my calculation here, okay? Because all we have at least 5, 5, 5, and then at least 5 squared in common. So I think I can factorize 5 squared. So I can calculate the other element better, right? This is my method. If you want to calculate directly, that's also okay. But I think will be a troublesome if you write in paper and maybe sometimes you're nervous. I think better to simplify it and then look at these uh, numbers, and eventually you get 25 11 over 12, or this will be 275 over 12, and you need to minus with the 1, right? Minus 1. This is the other equations, that is negative 19 over 12. So we will have this volume, and eventually we get 128 over 3 pi. So that's the solution. Okay. Okay. So I hope you already guess which graph that the shell method will be the only solutions. Okay. Because sometimes if you can do this method, I think that will be better calculations, easier to calculate usually compared with the shell method. Okay. The next one is you have to evaluate the integral. Okay. So here I take on two perspectives. Okay. So if you can do the DI method you get, and then you just plug in all the results, or you can also check with the regular integration by parts. Okay, and still it's actually similar results, okay, with our DI method. And eventually we get the same results, minus 2 pi squared. Okay. So that is our feedback time last Friday. Okay. Up until here, is there any question? Okay. I think last Friday we have discussed about the partial fractions, right? The partial fractions. Okay. In your textbook, I think there are a lot of sections explaining a method in partial fraction, but I think I can go into a practical example so that I think it could be simplified for you. Okay. Example. I think this is the last equation that I wrote for you, right? And then we can factorize the bottom part here. And then this is, I think we can also factorize. Last time, I think I already showed you this. And we can write down, this is A over X plus B over 2X minus 1 plus C over X plus 2. And then uh, we can calculate and determine A, B, C. Okay. So we are going to reverse and combine from this ABC element. Okay. So we combine and we are getting 2x minus 1, x plus 2, a plus b, this is x and x plus 2, plus c, this is x, 2x minus 1. And this should be equal with the numerator or the top equation. Yeah, I think this is the last Friday we already arrived at this point. Okay, let's try to calculate. Okay, 2x, 4x minus 1 is 3, so 3ax, and minus 2a. Okay, and then this will be plus bx squared plus 2bx. This is plus 2cx squared minus cx. And this will be x squared, 2a. Let's combine all the x squared, plus b plus 2c, okay? And then plus x is 3a plus 2b minus c, and then minus 2a. Okay, the idea is we need to solve this based on a system of linear equations. Okay, so we can have now 2a or minus 2a is minus 1. Okay, if you look here, it's the only constant that we got. So minus 2a is minus 1, or a is equal half. Okay, and we have 2a plus b plus 2c is equal 1. 3a plus 2b minus c is 2. Now we can plug in half into both of equations, and we will get this is the first one becomes a plus not a, it's 1. 1 plus b plus 2c equal 1. And then the second one is 3 over 2 plus 2b minus c is equal to, let's multiply by 2. 3, 6b minus 2c is 4. Then we can cancel this. And 3 going to be 4 here. 1. And we can write b plus 2c equals 0. 6b minus 2c equal 1. We can plus this. Oh, sorry. This should be 4. Let me check. 2, 4. Okay. So this is 4. So this is 5b equal 1. So b is 1 over 5. So 1 plus 1 over 5 plus 2c equal 1. Or this is 2c equal negative 1 over 5. Or c is negative 1 over 10. Okay. And we can plug in the results. Okay, we can plug in the results on the A, B, and C. So this is, we can write half 1 over 5 and negative 1 over 10. And we can actually write down the integrations of each element, for example. Or if you want to write this outside, also fine. It's a constant, so we can write like that. This is 1 over 2x minus 1, dx minus 1 over 10, 1 over x plus 2 dx. Okay, so the partial fraction is the idea to separate a big fractions, okay, into a small fraction, small fractions. That's the example, the first example. Now, second example, I would like to introduce you to the method called repeated linear factors. Repeated linear factors. Okay, the method is basically, let me just write an example here. Okay, now it seems that we already have a factorized element, okay, that we don't really need to be think how to separate. Okay, so if you look at this, okay, and you write, probably the first thing you can do is you can imagine this become, this is x squared plus this is x minus 1 cubed, right? This is the first thing maybe that in your mind, okay? But in repeated linear factors, In repeated linear factors, we can write this x squared and x minus 1 cubed becomes a many factors so that the top equation is just a constant. Okay. So if you have this, okay, at least the top should be a x, right? It should be, right? It should be here, like that. And this will be b x squared plus cx plus d. But it's still, if you try to integrate this is still a little bit complicated. The partial fraction, however, it needs or it makes the these big fractions become really really small. So it's not quite small here. It's not quite small. So we can separate this into different fractions. Okay? So we can actually separate this, become a over x, okay, plus b over x squared plus c over x minus 1 plus d over x minus 1 squared plus e over x minus 1 cubed. Okay. Now, if we take this as our separations, I think it will be better approach if we want to integrate the integral. Okay. And still, the idea on how to find a, b, c, d is similar. Okay. We can find and solve the system of equations, okay, for the linear equations that we have found inside. So for example here, a need to multiply with x, right, and then x minus 1 cubed, and then plus b, this is x minus 1 cubed, plus plus c, x squared, x minus 1 squared, plus d, this is x squared, x minus 1, and then plus e x squared. Okay. Okay, that's we can also do. Okay, another thing that probably I forgot to mention, because this part here, at least if you multiply the denominator, the x will be having polynomial 5, right, of degree 5. So the lower part is higher than the upper part. Okay. If the top equations, the numerator is greater, okay, so if if p degree is greater than q, we can do some long division. I think I already mentioned at the beginning, right? Long divisions. Okay. And I think we can also simplify the fractions. Okay. We can simplify the fractions. Okay. Okay. So this is called the repeated linear factors. Repeated linear factors. Okay. Another example. Okay, another example. Okay, we have those integral. Now, what will happen here is we look at the equation, the x squared plus 1, x squared plus 4. We call this irreducible factors. So this is uh, a case where we cannot factorize anymore, and it still has a quadratic equation. What will happen is if you want to write in terms of a, b, c, and the linear factors, we need to write in terms of first it's not a problem, still we can write the linear. But the second one, we need to write the bx plus c, because we cannot make it into separate factors. Okay. And the other one also dx plus e. Okay. Now, from here, we still have some problem to integrate if we have this integration here, right? At least if you have if okay, or if you remember tangent inverse x, okay, if you have the derivative of tangent inverse, remember that this will result on 1 over 1 plus x squared. Okay. So if you look at how the quadratics appear here, we will have x squared plus a something constant, and we call this irreducible constant, which is perfectly aligned with our derivative of tangent inverse x. So actually, we need to include the tangent inverse as our answers. Okay, most definitely that will be our answers. Okay, now if we have tangent inverse, but it's not x, but x over 2. Now what will happen? The equations become 1 over 1 plus, and this will be x over 2 and then squared. Or we can write x squared over 4 like that. And we need to multiply with the chain rule. Multiply with the chain rule is half. Okay? And then we need to solve a little bit. And this will be 4. 4 plus x squared multiplied by half. This is 2. 4 plus x squared. Now, if you look here, if you look this, and looking at this one here, x squared plus 4, okay? If this is just saying that we have x squared plus 4 like that, if this is the question, then we need to multiply with the half, right? We need to multiply with the half. So we need to multiply with 1 over 2 to make it equal, right? If this is what we need to find, we need to multiply by half. So, okay, so from here we get the idea on general formula of the x. This is x squared plus a squared. A is a constant. And this will be resulting 1 over a, right? Because of the chain rule. and this will be tangent inverse of x over a plus c. So if you have, for example, dx x squared plus 5, for example, this will result 1 over square root of 5 tangent inverse x over square root of 5 plus 6. Okay. Now, I hope this is helpful for any irreducible factors. Okay. If you have any questions, you can write on the text box. The upper from here. Okay. So the top one is the repeated linear factors that we can separate perfectly aligned and with the top equation as a constant, right? The bottom one here, this is where we call the irreducible factors. And one way to solve this x squared plus 1 for the denominator is if you look at the tangent inverse. So it might be our solution for the 1 over 1 plus x squared. And when we have, if we imagine maybe we have x squared plus 4, okay? One way to imagine is actually the formula is like this, right? The formula is like this. But I don't want you to be burdened or taking too many memorizations, formula. One idea to make this happen is you can differentiate tangent inverse x. This is just a simple perfect like this, right? But if you differentiate tangent inverse x over 2, you need to differentiate, take this element squared, right? And then you need to multiply with the chain rule, which is half. Okay? And if we try to solve this or simplify it and rewrite the form, it will be like this. Okay? And we can simplify become this. Okay? So if we have 1 over x squared plus 4, we need to multiply with the half to cancel these two, right? Okay. So that's the I think reasonable process for going through to solve the quadratic integral. Okay. So that's why we came with this formula here. Okay, so this is the irreducible factors. The other case, okay, the last case in partial fractions is when you have the irreducible factors, sometimes these irreducible factors can be repeated. Okay, so we call them repeated irreducible factors. It's called the repeated irreducible factors. So for example, we have a really big, really long okay. Now the repeated irreducible factor is this one. So if you need to separate all of this, then this should be a over x plus b over x minus 1 plus this is the irreducible factor, so we need to write the cx plus d. This is x squared plus x plus 1. And the last one here, it is x squared plus 1, but it has a cube, so we need to write 3 times. So first is ex plus f, x squared plus 1, okay, plus gx plus h. This is x squared plus 1 cube plus ix plus j. This is x squared plus 1 cube. It is this just as to show you how we can have the irreducible factors, but we have repetitions of it. I think this is a better approach. Instead, like if we check this x squared and then cube, so we need to have x with power of 6 at least, right? So our top equation, if we just write as it is, we need to have power of 5, right? And I think that will be still very complicated. So I think we can still just take it into this one and maybe still complicated, but less complicated than if we take the whole thing, the cube thing here, okay, the x squared plus 1 cube. I think that's already complicated. And that's it, the partial fractions, okay? So the idea is to separate the big fractions. If you can factorize, you need to factorize first. If you can do long division, you can do long division and simplify the form, and hopefully it can be easily to be integrated. And the key in the partial fraction is the repeated factors. Okay, the repeated factors. Either it's linear or it's irreducible factors. If you do the repeated factors, you can separate the the big fractions become very, very small, very, very small, and hopefully it can help for the integrations. Okay, the rest is you need to use some techniques, okay, that you already learned. Okay. Okay. I think that will be the partial fractions. Like I think later I can maybe tomorrow I will maybe put some practice for you. So in chapter 7, this is chapter 7.4, I think. 7.5, it's about strategy for integrations. Not really that matters. It's just a discussion on how to solve the integral. 7.6 also not really matters. It's integration using tables and technology. Not really matters in our class. We can skip those two sections. 7.7, this is approximate integration, but I think I will skip for now. I will skip for now. This is actually similar with our definite integral, but it has another method like the midpoint, the trapezoidal. We can skip for now. At least we understand the basic on how this integral came from through approximations, through the sum. Okay. So plus 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 the area under the curve, right? So we can skip for now. Okay, I think we can take short break, 5 minutes, 5 minutes short break. And while we so let me write the 7.8. It's called improper. Okay, we can have a 5 minutes break. Okay, there's a question. How to prove all P over Q can turn into the form of partial fraction? Okay, there is uh, some notes actually about the partial fractions that I didn't really mention. Um, so we need to make sure actually so if we have the P over Q, we need to prove first that Q is a product of linear factors. And if the Q is having irreducible factors, then one way to look at is this can be irreducible factors. if the determinant or the b squared minus 4ac is less 0. This is from the quadratic equations ax squared plus bx plus c. So we need to prove that it has the linear factors. Okay? So when it doesn't have, we cannot do any uh, partial fraction. So you need to make sure that we can factorize at least, okay? Or we can have some linear factors. Okay? So that's how partial fractions work. So we need to make sure that we can have factors. Okay? I hope that's answer. Okay. So most of the example that I showed you, that I showed the factors already, right? Like this one, and then the other one is like this one. It's already a factors, so that's why we can directly take it into partial fractions. Okay. And if you want to check whether our uh, equation correct, then we can reverse the equations, whether we are going back to the original equation or not. I hope that's answered the question. Okay, I think we can look on the next sessions on chapter 7, which is it's called the improper integral. Okay. Basically, we have two types. Okay, two types. The first type is we call this infinite interval. So why it's called improper integral? Okay, because the situations. Okay, the first one is we have an integration from a to infinity. And the second is the functions has discontinuity in a b. A a less c less b, and the f of c is undefined. Okay, this is called improper integral. So that's we are going to integrate, but uh, with some rules. Okay, because it is not usual integrations. We're going to integrate with the endpoint. One of the endpoint is infinite, or both endpoints are infinite, or if the function has a discontinuity, then what will happen? But still, because basically, if we remember how how the integral is came from the definite integral situation, which is it has definition from the sum, right? From the sum, then these two cases we can at least try to getting closer, getting closer. Okay? And how to get the closer? We can use limit. Okay, basically, we can solve most of the problem with limit. Okay. Okay. As introduction, let me draw the graph of 1 over x squared. Okay, let's say this is y equal 1 over x squared. Okay, and the question is, if I evaluate this integral, this area, from 1, the question is, if we try to evaluate from 1 to infinity of 1 over x squared, what will be our result? Okay. So as an illustration, let's just take our area here and take some points maybe around here. Let's make it P. Okay. So we can have the area, okay, as 1 to t of 1 over x squared dx. Okay, let's just integrate as usual. So this will become a negative 1 over x from 1 to t, or if we going to input, okay, this will be uh, or this will be 1 over 1 minus t, right? Okay. From these expressions, okay, before we going to state what is our answer exactly, if we look at this, 1 minus 1 over t. So as t getting increased, the area, okay, should be less than 1, right? Should be less than 1. Okay, that's our criteria here. So the area is, of course, logically, it's always less than 1, right? So if we try to take the limit as t approaching infinity, okay, of our area, we get the notions that when t is getting larger, this t getting larger, is getting to be close to 0, right? If we remember the limit concept at the beginning of our class, right? So we can say that the area will become 1. These results showed us that there will be some results within these functions or this integral. Okay. We call these results as converge results or convergent. Okay. Okay, that is the 1 over x squared. Okay. The result is convergent. If you try a similar idea, but the function is 1 over x, okay, what will happen? 1 over x. It will be ln, right? What will happen? Yes. So that means we are not getting any results. Or we call the results is diverge. It's diverge become not really getting to one exact solutions that, but it's getting just diverge. Okay. So this will be getting limit as t, but this is a proper way to solve. Okay, so because we cannot use any infinity inside the equation, right? So we need to have some variables, okay? And this is a proper way to do it. for improper integral. We need to include the limit at the very beginning. Okay? Because if we try to integrate this and still we have this infinity here, it's actually we cannot, it's a little bit, we say in the calculus, this infinity is exactly an not an actual number, right? So we need to take it into some variable and then take the limit for that variable approach infinity. And this is, we can do this way, I think better way. So this will be ln from 1 to t. So we will have, still we have limit. And from here, we know that this getting an infinite result, or we call the result is divergent. If you look up the graph for the 1 over x, you see that the gap is still big compared with the 1 over x squared, which is getting small. Right? It's getting real small, okay, very fast, small very fast, but 1 over x still has some gap, and if you continue, it still have a gap. Okay? So that's why it's getting infinite results. Okay, let me give you some theory on how we should write the process. Okay? This is just an intro for to look on the improper integral and some of the results that might be in our solution, which is a convergent or divergent. Okay, now definition. Okay. This is the type 1. Type 1 is infinite interval. If integral from a to t of f of x dx, if the integral is exists for every number t greater or equal a, then we can write this in terms of the limit as t approaching infinity and provided that the limit exists. If this is another form we have a negative infinity, or every number t greater equal t, then and also it needs to be provided that the limit exists. And then we call the improper integral of a to infinity of f of x dx and integral from negative infinity to b of f of x dx. We call from here, we can call it convergent, and we can call it divergent. Convergent if limit exists, divergent if limit doesn't exist. And last one, if both integral if both converge, then we can define oh, I think this is not B, it's A. Where A is real number. Okay. So what this theory tells us is first how to define whether the limit exists or doesn't exist, and we can define that limit as our integral results. Okay, and if the results both this form are converge, okay, if we happen to have this problem here from negative infinity to infinity, we can separate this integration and we can solve each one, okay, and we can solve each one by limit, okay, by limiting each integrations here. So eventually we will get the limit. Let's say we have t or maybe the other one is maybe taking other forms. You can write with other variable as well, as long as it is uh, still uh, still okay to define. Okay? For example, if you maybe confuse, this is the one is T, the other one maybe U, I think that's also okay, or P, that's also fine. Okay, now back to the 1 over x and 1 over x squared. Okay, let me go back to just a reminder for 1 over x. This is from 1 to infinity and 1 infinity for 1 over x squared dx. Okay. Now at least from these two kind of functions, we can have one general form. Let's write 1 over x with power of p. Okay. Now, if we try to make some general formula, let's try to take it as a limit. And let's take the integral. Let me write one by one process. Okay. So the integrations will be, still we have to write the limit. So this is minus p plus 1, or 1 minus p, like that. And then over 1 minus p. And it's from 1 to t, right? Now, because p is a constant, we can factorize 1 over 1 minus p outside, still to have limit, or maybe limit is inside. I think it's okay. And we put the t and 1 to x. Okay. So it will be 1 over t, p minus 1, minus 1. Okay, now the idea becomes, okay, if p is greater than 1 or less 1, if we can check. So p minus 1 is greater than 0. As t is getting or approaching infinity. So t with power of p minus 1 is also getting infinity, right? Because p is positive. So 1 over tp minus 1 becomes 0. Okay? And remember, okay, we can do all of this because of this is limit. Okay, this is limit. So we can do all of this. Okay. So this will be getting result 0. So when this is 0, then the results, so this is equal 1 over p minus 1 if p is greater than 1. Or we call this is converge. So converge if p is greater than 1. You can check the other one if p less than 1. Or even if p equal 1. And if you look at this will be diverge. Okay, let me give you maybe a little bit example. Maybe 2 example. Okay, let's try this 2 example. I maybe try to solve it first, giving some few minutes to check. Okay, I think not too difficult. I think both of this example can be solved by substitutions, right? Substitution. But the other problem is it has the improper method. So the first thing you need to do is you need to take it as a limit. Okay? Take it as a limit and exchange this infinity into other variables. You can take limit approaching this infinity, and then we can solve just as usual substitutions method. Okay, so first we take this as a limit, and then we can solve, or we can check the integral first without the endpoint, and then after that we can exchange the result with the improper one. Okay, but in case you want to take this inside this limit, it's still doable. We can take the substitution method. So we will have u, if x is e, then u is 1, right? If x is t, then u is ln t. So we will have 1 to ln t, 1 over u cubed du. And this will result in still we have limit. Don't forget we always to include the limit. Minus plus, okay, plus half. If you look here, this will getting 0, right? So this will be resulting in half. So we call that the limit is, or the result is it's convergent results. It's a converge. Okay, the second one, I think you can try by yourself. The result is diverge, right? Diverge. You can check by yourself here. Diverge. Okay. Okay, let me take the definition for type 2. So if functions is continue on A, B like that, okay, and this continue at B, okay, then the integrations will be, we need also to write the limit as, let's say t, in our case, this is from the left, okay, and this will be A, B, and then f of x dx. So we need to imagine, okay, where the limit comes from. Okay. from the left, from the right, depends on where the point is getting discontinuity. Okay, this is provided the limit exists. Okay, provided the limit exists. So if f is continue on, now discontinue at a, then this is limit st approaching a from the right. Okay. And provided both limit exist. Okay, provided both limit exist. And if limit exists, still we call it a convergent. If limit doesn't exist, we call it divergent. See, if functions has discontinuity at c, that c is in between a and b, then we can write ac, a to c, f of x dx, and c to b f of x dx. If both of this converge, then we can write this in separate integrations, and we need to provide it first that both of this integral it's converged so that we can separate the integral. Okay. I think that is for the theory. Okay. For I think for the basic improper integral. Okay. We still have at least one little section on this improper integral. If we call the comparison theorem, and I think I will show you next week, okay, when we have a quiz. Type 2 is when we have discontinuity. Yeah, I think that's it for our class today. Yeah. Improper integral. So I will give you some exercise on partial fractions and improper integral. Hopefully tomorrow I will upload on the Google Classroom, and maybe giving you some additional video maybe on Wednesday or maybe tomorrow. Some review on chapter 6, and also maybe some overview of chapter 7. Okay, now we will have feedback time for today. But before that, is there any other question? Okay. I hope I can make additional video, at least 2 videos for this week, okay, to help you first review chapter 6 and maybe the other one for overview of chapter 7. Okay. I think the idea for the integrals is the more you learn about the technique of integrations, the more you practice for some problems, you will be more familiarized. You will be getting used to how to solve the integrals. I think it can help you to solve most of the problems. Okay. Okay, I think I can give you the feedback. Yeah, and I think uh, yesterday and tomorrow is really cold, right? So you need to also to get some make sure you have cold jacket. Okay, our feedback is mostly about the technique of integration, integration by parts, some theory, because I would like to know what we have learned since last week and maybe last 2 weeks. Okay. Okay, I think we can go. All right. Uh, okay. I hope you guys ready. 3, 2, 1. Okay, let's go. 3 question. Is it just a true or false? And I believe we already did this. I'm not sure. Okay. Yeah, it's true. Okay. Okay. Okay, 3, 2, 1. I have still remember, and I hope the time is okay. 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 I think good. Let's see. Okay. The last one. Okay, 1/24. Yes. Okay, here? No, not here, right? Okay. Okay, so yeah, this will be the end of the lecture today. Uh, Hopefully, I can give you more additional lecture this week for reviewing chapter 6. Okay, scan QR code. Wait. Okay, see you next Monday because this Friday is holiday. Okay, this Friday is holiday.